Welcome to Lecture 19, which is about the implementation of arbitrary two-level unitary transformations. In other words, we're thinking about the idea of we have a unitary transformation and we want to actually implement it as a circuit. And this is discussed in your textbook, and frankly, I think that it's a pretty challenging to follow the topic as it is discussed in your textbook, and I think that you might find it easier to look in the book Quantum Computation and Quantum Information by Nielsen and Chuang. If you look at the 10th anniversary edition, then this material that I'll be discussing is on pages 188 to 194. You don't need to go and look at this. I think that the discussion here will be self-contained, but if you would like to look at that, I certainly welcome you to do so. And because this is a somewhat involved lecture, I have gone ahead and written it out in advance. Maybe I should take a break until the dogs stop, because this is hard enough as it is without the competition from them. Okay, so we begin with a definition, which is that a two-level unitary matrix is simply a unitary matrix. Remember, we've discussed these before. It's a unitary matrix that acts non-trivially only on two or fewer vector components. And that is, in all but two or fewer of the rows of the matrix, and columns as well, all the entries are 0 except for the diagonal entry, which is 1. And so we have here an example of a two-level unitary matrix. You can see that in all of in the second, third, and fourth rows, the only non-zero term is a 1 in the diagonal. And the only rows or columns that don't act non-trivially are the first and the fifth. And what we mean by non-trivially is the following. If you use this matrix to pre-multiply this vector x with components x1, x2, x3, x4, and x5, and you call the resulting vector y with components y1, y2, y3, y4, and y5, you'll see that y2 is equal to x2, y3 is equal to x3, y4 is equal to x4. Those three components will be unchanged. The only components of the y vector that might be different from the corresponding components of the x vector are y1 and x1. They could be different, and y5 and x5. But x2, x3, and x4 would be equal to y2, y3, and y4, respectively. So that's what we mean by acting trivially or non-trivially, and this is an example of a two-level unitary matrix. And the importance of this, of a two-level unitary matrix, as we will see, is that these can be implemented using gates that act only on one qubit. Now, so after this discussion of what a two-level unitary matrix is, then it says, now let's see how to implement a two-level unitary transformation. And so we're going to just make an example here. We'll be discussing this topic through the use of examples. And so suppose that we want to implement a unitary transformation that acts as follows. It acts, you might say, trivially on 0, 0, 0, 0, 0, 1, 0, 1, 0, 101, 110, and 111. And what I mean by that is that in each of those cases, it just gives back the same state. U of 000 is 000, U of 001 is 001, and so on. But on two states, it acts in a non-trivial way. U of 0, 1, 1 is equal to A times 0, 1, 1 plus B times 1, 0, 0. And U of 1, 0, 0 is C times 0, 1, 1 plus D times 1, 0, 0. So we want to figure out, now this is a two-level unitary transformation, and we want to figure out a circuit that will implement this. And in the problems for this lecture, we'll have a similar kind of situation, and you should go through the procedure that is outlined as follows. The first step of the procedure, let me take a break again. Okay, the first step of the procedure, it says we will use the standard basis for 3-qubit states, but not in the usual order, which is used above. Yeah, what I mean here is you see that we've listed everything here in the usual order, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. So we've followed that usual order, but we're not going to follow that usual order here in step 1. What we're going to do is instead we will use a gray code to reorder the bases. Now, a gray code is a sequence of lists of bits, and each list differs from the previous and subsequent lists only in one position. And here's an example of what we mean there. Okay, so this here is a gray code. We start with some list 0, 1, 0, 1, 1, 0, 1. And then notice that this next list differs from the first list only in the first position. And so that's why I've written over here, these two lists differ only in the first bit. Then for the second list and the third list, you'll notice that they differ only in this position, which is the 6th bit. And for the last two lists, they differ only in the 3rd bit. So since it is the case that each one of these lists differs from the following one only in 1 bit location, this is a gray code. So now we want a gray code for the states, and as I said, we're going to use the standard basis. So we're going to use these same states here, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. We're going to use these states, but just in a different order. Now, as this note says, you can start with any state you wish. And some people might suggest you start with one of the two states upon which U acts non-trivially, but as we will see, this is not necessary. So we're going to start with 0, 0, 0. Now, notice that U does not act non-trivially on 0, 0, 0. It acts trivially on 0, 0, 0. That is, it just gives back 0, 0, 0 when it acts on 0, 0, 0. But that's okay. If we adopted the idea that we would start with the first state upon which U acts in a non-trivial fashion, then we would start with 0, 1, 1. And that would be okay. And in fact, you might want to practice by doing that. But that's not necessary. So we're just going to start with 0, 0, 0. And there's a lot of variation in terms of how we could go here with this gray code, but I'll change the last bit. So we go from 0, 0, 0 to 0, 0, 1. And then I'll change the middle bit, so we get 0, 1, 1. Then I'll change the last bit again, so we have 0, 1, 0. Then I'll change the first bit, so we get 1, 1, 0. then change the middle bit so we get 1 0 0, and then change the last bit so we get 1 0 1, and finally change the middle bit so that we have 1 1 1. And notice that here we don't have any repetition of states, and we have simply now reordered the states, and the ordering is shown right here. And so, since we've reordered the states in the basis, now this means that the vectors associated with these states will not be the same as they are when we have the usual ordering. Now, the vector associated with 0 0 0 will still be 1 0 0 0 0 0 0 0, and this t means transpose. So it means it will be the instead of this row vector, when we transpose it, we'll get the column vector that has 1 in the first entry and then 7 zeros. And that's what we're accustomed to for the vector associated with this state when we're talking about 3-qubit states. So that's fine. Nothing surprising there. And in fact, this is the vector. Again, notice that each one of these vectors has been transposed, so each one is really a column vector. This is the usual vector associated with this state here, the second one. And furthermore, this last vector, which is 7 zeros and then a 1 in the last term, that is the usual vector associated with this, with the state 1 1 1. But some of these other states are getting associated with vectors that are different from what we have in the usual case. For instance, 0 1 1 would ordinarily be associated with a vector having 3 zeros and then a 1 in the fourth location and then 4 more zeros. But with this gray code ordering, we have a 1 in the third position and then 5 zeros and so on. So you can observe that with this ordering, of course what we're doing here in these vectors is just for the order tells actually also the position of where the 1 will be. So in the first term or the second term or third or fourth or fifth or sixth or seventh or eighth term. So these will be the states and in the basis, and this is the ordering, and so these are the vectors that we associate with those different states. So now, if we wanted to find U, the matrix for U, then we would proceed as follows. Okay. First of all, U of 0 0 0 is equal to 0 0 0. And 0 0 0 is the first vector. So it says that U of the first vector is equal to the first vector. And so we have 1 here in the first column, and all the rest are 0. Now the second vector is 0 0 1. And we come back up here, 0 0 1 gets mapped to 0 0 1. So that means that in the second column we have a 1 in the second row. What about for the next column, which corresponds to column 3? Well, column 3 is state 0 1 1, and state 0 1 1 is getting mapped to A times 0 1 1 plus B times 1 0 0. Now 0 1 1 is the third vector, so we have A times the third vector. What is 1 0 0? Well, if we come down here and look, 1 0 0 is the sixth vector. So 0 1 1, which is the third vector, 0 1 1 is the third vector, is getting mapped to A times 0 1 1, so that's A times the third vector, plus B times 1 0 0, which is the sixth vector. So we have A times the third vector plus b times the sixth vector. So we come over here to the third column of u, and it will have an a in the third row and a b in the sixth row. Now, what about the fourth column? Well, the fourth column is corresponding to 0, 1, 0. And 0, 1, 0 is getting mapped to 0, 1, 0, which is the fourth vector. So we just have a 1 in the fourth row and a 0 everywhere else. What about the fifth vector? The fifth vector is 1, 1, 0. We scroll up. 1, 1, 0 is getting mapped to 1, 1, 0. So we just have a 1 in the fifth row of the fifth column. Now to the sixth column. The sixth vector is 1, 0, 0. And if we look above, 1, 0, 0 is getting mapped to c times 0, 1, 1 plus d times 1, 0, 0. And as we found out before, 0, 1, 1 is the third vector. 1, 0, 0 is the sixth vector. So this is c times the third vector plus d times the sixth vector. So in the sixth column, we will have a c in the third row and a d in the sixth row. For the sixth column, that's 1, 0, 0. Seventh column now. We just did the sixth column. For the seventh column, that is 1, 0, 1. And u of 1, 0, 1 is 1, 0, 1. So that's vector 7. And so we just have a 1 in the seventh row of the seventh column and a 0 everywhere else. And finally, for the eighth column, vector 8 corresponds to 1, 1, 1, and 1, 1, u is mapping 1, 1, 1 to 1, 1, 1, which is the eighth vector. So we just have a 1 in the eighth row of the eighth column and 0 everywhere else. So here is the matrix for this transformation with respect to the basis ordering that we've come up with right here using the gray code. This is the matrix. And as predicted, we can see that this is a two-level unitary transformation or a two-level unitary matrix here. And U acts non-trivially only on the third and sixth components of vectors. And I guess I should say here, U will be unitary provided that U tilde, which is these symbolic terms, A, C, B, and D. I've grouped them all together. The overall matrix U will be unitary provided that U tilde is unitary. Okay, so now that we have used the gray code to reorder the basis, and by the way, let me note one thing. This step here of finding the matrix for U was not necessary. We do not have to do that. All you really have to do in step 1 is to come up with a gray code that will give you an ordering for your basis. Okay, that's all you have to do in step 1. Now, I guess I should say it's useful. You do need to know what this U tilde matrix is, but I think you can find that out. You could reason what that will be just from this information. You would not. I mean, I'll admit, writing out all of U it certainly makes U tilde very obvious, but I think you could find U tilde without doing that. You'd have to be careful, but I think you could do that. Okay, so however you find U tilde, we'll now proceed to step 2. Step 2, we find a gray code again, but this time remember in the first case, the beginning list was any state we wished. But in step 2, the beginning list is the first state that is non-trivially transformed. And the last list will be the second state that is non-trivially transformed. So if we come up here and remember that 0, 1, 1 refers to the third, is the third vector or third entry, and 1, 0, 0 actually is the sixth, then obviously 0, 1, 1 is the first state that is non-trivially affected. 1, 0, 0 is the second one. So we want to find, in step 2 here, we want to find a gray code that has 0, 1, 1 as its first list and 1, 0, 0 as the last one. And here is one possibility. This is not the only possibility. There are others, and I encourage you, if you wish to, experiment with some other possibilities. But this is the possibility. This is the ordering that we will use for this example. So as it says in this case, the first state that is non-trivially transformed is 0, 1, 1, and the second is 1, 0, 0. So a possible gray code is this. And now once you have that gray code, the final step, step 3, is to construct the circuit. Believe it or not, you're already ready to do that. And let's see how it goes. It says the left half of the circuit will transform, one step at a time, the first state into the next to last state. Then apply U tilde to the bit in which the next to last state and the last state differ. Then the right half of the circuit will undo the effects of the left half of the circuit. Now let's try to understand what that means. But first, I want to get some notation. We're going to use the following notation for multiply controlled gate. So here is an example of a multiply controlled gate. We have looked in class already at singly controlled gates, but now we're looking at a multiply controlled gate. And what this means is that both, in this case, both of the first two qubits, their values control what's happening here to the third qubit. And so the third qubit, when we go through this X, it will remain the same. It will always remain the same, except in this case when the first qubit is 1 and the second qubit is 0. And in that case, when the first qubit is 1 and the second qubit is 0, then the third qubit will toggle or flip. Similarly, if we had this multiply controlled gate, and let me okay, so if we had this multiply controlled gate, then what happens is that the second qubit will go through unchanged in all cases except when the last qubit is 1 and the first qubit is 0. In that case, the second qubit will toggle or flip, but in all other cases, the second qubit will remain unchanged. So that's the notation that we will be using for these multiply controlled gates. And now I claim that the circuit we want is the circuit given right here. And let's see how this is obtained. Well, let's refer again to our gray code. The first thing we want to have happen is 0, 1, 1 must go to 0, 1, 0. So if you look at those two lists, you see that what is happening is that when the first two bits are 0 and 1, the third bit is toggling. So that's why the first element here is this. We have the toggling of the third bit only when the first bit is 0 and the second bit is 1. Again, look at this. For both of these, the first bit is 0 and the second bit is 1, and we toggle the third bit. So that's why we have 0, 1, and then toggle the third bit. Now, the next gate will get us from here to here. And notice what's different. What is different between those two? Well, the second bit is equal to 1, the third bit is equal to 0 in both of them, but we're toggling the first bit. So we come down, and sure enough, we see toggling the first bit when the second bit is 1 and the last bit is 0. Second bit is 1, last bit is 0. Second bit is 1, last bit is 0. And that, so this gate, which I've labeled G2, will get us from here to here. Now, when we get to this next to last state, and notice this is what this is saying, the left half of the circuit will transform. The left half is this G1 and G2. The left half of the circuit will transform, one step at a time, the first state into the next to last state. So that's what we've done. G1 takes us from this state to this state. G2 would take us from this state to this state. This is our next to last state, so we stop at that point. So the left half of the circuit will transform one step at a time the first state into the next to last state. Then apply U tilde. Remember U tilde up here. It says apply U tilde to the bit in which the next to last state and the last state differ. Now, if we look at the next to last state and the last state, they are differing in the second bit. So we will apply U tilde to the second bit, but only when the first bit is 1 and the third bit is 0. So you see here we have first bit is 1, third bit is 0, and here we have this A, and it says that, well, actually, let me change that. We'll just make this U tilde. So again, we apply U tilde to the bit in which the next to last state and the last state differ. They differ in the second bit, so we're going to apply U tilde to the second bit, as you can see, but only when the first bit is 1 and the last bit is 0. So that's why we have the 1 and 0 there. And then it says, then the right half of the circuit will undo the effects of the left half of the circuit. So what does that mean? We just repeat the elements of the left half over here and the right half in reverse order. So we had G1, G2, now we have G2, G1. And believe it or not, that's the end of the procedure. And the claim is that this will implement the transformation that we wish. There's only, well, there's one last issue that we need to deal with, but we'll deal with it in just a moment. So I hope that you're skeptical. I hope you don't just accept this. And so let's see about this. Let's check it and see how it works. Now I'm going to list this first gate I'll call G1, the second one is G2, this one is G3, this one is identical to G2, so I'll just call it G2 again, and this one's identical to G1, so I'll use that label again. Now to get an overall picture of what this whole, what we're claiming is that this whole circuit implements the transformation U that we have right here. And to check and see if that's right, we'll need to try each one of these states and see what happens to it when it goes through this circuit. So that's what we're going to do here. We're just trying all 8 states and seeing what happens when we put them into this circuit. And by the way, I've used, for the sake of comparison, I have I have the states up here listed in this order, and so I listed them in the same order down here. But in some ways, it would be more convenient just to use the order specified right here. But of course, in the end, the transformation must act in this way. So let's see what happens. And I don't believe we'll need to do every single one of these before you get the idea. So let's say, okay, we have 0, 0, 0 coming into G1. And since the second bit is 0 instead of 1, we can immediately say there will be no change. So 0, 0, 0 will go to 0, 0, 0. What about 0, 0, 1? If 0, 0, and I'm just going to take this one step at a time. So what if 0, 0, 1 were coming into gate 1? Well, again, since the second bit is 0, nothing will change. So we get 0, 0, 1 stays as 0, 0, 1. What about 0, 1, 0? Well, 0, 1, 0, the 0 and the 1 match, and so that 0 will toggle, and 0, 1, 0 will become 0, 1, 1. And indeed, that's what we have here. 0, 1, 0 will become 0, 1, 1. What about 0, 1, 1? Well, the 0 and 1 match, so 0, 1, 1 goes to 0, 1, 0. That, the last bit will get toggled here from 1 to 0. And then for all the rest of them, there will be no matching. And so what we conclude then is that G1 acts trivially only on 0, 1, 0 and 0, 1, 1. And it will map 0, 1, 0 to 0, 1, 1 and 0, 1, 1 to 0, 1, 0. But all other states will be mapped to themselves by G1. Now, what about G2? Well, I think you can see, thinking those same lines, G2 will act trivially, non-trivially on a state only when its second bit is 1 and the third bit is 0. So let's look at states that match that. Here's 1, 0, and so it goes from 0, 1, 0 to 1, 1, 0. And here's another 1, 0, so it goes from 1, 1, 0 to 0, 1, 0. But all other vectors will map to themselves, as you can see. So that takes care of G2. And now, then we have these vectors coming into G3. Now, since G3 has a 1 up here in the first bit and a 0 in the last bit, there's only 2 states that will be non-trivially affected by G3, and that's these 2 right here. And it is no accident that these 2 appear consecutively. That has been the effect of G1 and G2, is to make these 2 consecutive states. Notice that G3 has no effect on the other states. Only on these 2. Now, remember, G3 is really the first bit, and the last bit will just be passed along. It's that second bit that will get acted on by U tilde, which we have up here. But we need to be careful. What we have to ask ourselves, what, is just like up here when we calculated the matrix for U, we found that we had to take into account the ordering of the basis in order to determine where the entries in this matrix went. And so likewise down here, for U tilde, we know that the U tilde matrix is right here, but what is the ordering of the basis now? Now this is acting only on the second qubit. Remember, this is acting only on that second qubit. And what is the ordering? Is it 0, 1, or is it 1, 0? Well, if the ordering is 0, 1, then as usual, then this first column would be the image of 0, and the second column would be the image of 1. So U of 0, so with U tilde, we would have U tilde of 0 is A times 0 plus B times 1, and U tilde of 1 would be C times 0 plus D times 1. That's what this would mean if the ordering of the basis is 0, 1. But if the ordering of the basis is 1, 0, then that means that this is the image of 1, and this is the image of 0. And furthermore, the first entry is 1, and the second entry is 0. So in other words, we have here the image of, or U of 0 is C times 1 plus D times 0, and U tilde of 1 is A times 1 plus B times 0. So you need to pay attention to what the ordering is of this basis for the second qubit. Well, where do you find that out? Well, the answer lies in this gray code that you used to transform from the first non-trivially affected state to the last non-trivially affected state. In looking and determining the basis for that one bit upon which U tilde acts, you need to look at the last two entries here in that gray code. Look at the bit in which they differ, which is the second bit. And we have 1 and then 0. And so that gives you your answer. Since it's 1 changing to 0 instead of 0 changing to 1, if it were 0 and then 1, then this is our basis. And these equations would give the effect of U tilde on 0 and U tilde on 1. But since it is 1 changing to 0, then our basis is 1, 0. And we have U tilde of 0 is C1 plus D0. U tilde of 1 is A1 plus B0. That's the only tricky part of this. So when we come back down here for the effect of G3, now remember, we've already argued that because of the 0 here and the 1 here, that G3 will only affect the two states 110 and 100. And now we have found how G3 will act on the second qubit, which after all is the only qubit in which these two states differ. It acts on this 1. U tilde of 1 is A1 plus B0. So we get A times 110 plus B times 100. Again, think of this as, notice that the 1 in the first qubit and the 0 in the last qubit, they're just coming along for the ride. It's only the second qubit that is getting acted upon by U tilde, and U tilde acts on 1 by giving A times 1 plus B times 0, as is indicated here. And on the other hand, down here for this state, the initial 1 and the final 0 are just carried along. But now 0, When the second qubit is 0, how does U tilde act on 0? Well, U tilde of 0 is C times 1 plus D times 0. So we get C times 1, 1, 0 plus D times 1, 0, 0. And then everything else will be unaffected. And once we have completed that, then we start undoing our changes. And so we use G2 and G1, and of course they act just as they did before. And notice now that acting on a sum, we just, okay, here, for instance, let's look at G2 acting on A times 1, 1, 0. Okay, for G2, if you have the second bit is 1 and the last bit is 0, then it will toggle the first bit. So 1, 1, 0 will become 0, 1, 0. But the 1, 0, 0 is unchanged. So the A110 becomes A010. B100 just stays B100. And likewise, C110 becomes C010. But again, D100 it just stays as D100. And then G1 will act on this, and since we have 0, 1 here in this term, then this will become, the third bit will toggle, so we get 0, 1, 1 for both of those, but again 1, 0, 0 is unaffected. And so this is a detailed description of how this circuit will work. And now if you compare the extreme left-hand side of this chart with the extreme right-hand side of this chart, you will see that indeed this circuit is acting in exactly this way. So, as noted here, note that this matches exactly. So now for some problems, and we're going to look at an easier case in the problems. Suppose we want to use this same procedure to find a circuit that will implement the following transformation. Here we just have a 2-qubit state, and the transformation will map 0, 0 to 1 over square root of 2, 0, 0 plus 1 over square root of 2, 1, 1. It'll map 0, 1 to 0, 1. It'll map 1, 0 to 1, 0. And it will map 1, 1 to 1 over square root of 2, 0, 0 minus 1 over square root of 2, 1, 1. Now, suppose that in step 1 we use this gray code to order the basis, and that in step 2 we use this gray code. Notice that the first entry in this gray code is the first state that is non-trivially affected by U, and the last state in that code is the second state that is non-trivially affected by U. And so we're going to use this gray code for that in step 2. And I'm claiming that if you do that, then the circuit that you will obtain will have this form: G1, G2, G1. And so now your problems. 19.1, what is G1? Here are your choices: A, B, C, and D. Oh, and I should have that for C. Okay? So what is G1? 19.2, what is G2? In each case, the boxed term is U tilde. So which one of these is correct for 19.2? And then for 19.3, using the basis ordering specified in step 1, what is the matrix for U? Here you have 4 two-step unitary matrices, which one is correct for this transformation? And keep in mind now, you must use the ordering, basis ordering specified in step 1. And then the final remark is this: I'm asking you to keep a record of your answer for the in-class problems. And I mean for this, your answer to 19.3. Keep a record of your answer to 19.3 for the in-class problems. We will call this matrix MU. Since it's the matrix for U, we'll call it MU. To do the in-class problems, you will also need the matrices for G1 and G2 with respect to the basis of step 1. We will call these M1 and M2 respectively. You might as well calculate these in advance. And then I'll have you do just a little bit of calculation with those matrices on the in-class problems. So that concludes this lecture, and good luck.